Bombay, TIFR Mumbai, and a faculty associate at ICTS Bangalore. And he was earlier with Microsoft Research in Bangalore, and he obtained his MS and PhD in ECE from UT Austin, and BTech and EE from IIT Bombay before that. And he has several awards and honors. He is a co-recipient of the IEEE Signal Processing Best Paper Award 2019, Indian National Science Academy Medal for Young Scientists, and was an associate of the Indian Academy of Sciences. His research interests are these days in make training and inference of large language models more efficient. Over to you, sir.
Thank you, Professor. Hello. 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 Is this okay? Thank you, Professor Shalab, for the introduction, and thanks to Gagan and Professor Shalab for inviting me and for organizing this wonderful workshop. So in this talk, I'll be talking about second-order methods for bandit convex optimization and control. And this is actually joint work with my wonderful collaborators, Arun Sai Sugala, who is also my colleague at Google Research India, Jennifer Yu, who is a PhD student at Princeton University, and Gilad Azan, who is also Jennifer's advisor, he's faculty member at Princeton University, and also leads the Google Research lab at Princeton. Okay. So this is a broad outline of my talk. I'll first introduce the problem of bandit convex optimization. And this is a very rich, this is a very well-studied problem with a very rich history. So I'll overview some of the history and related work on this topic, and then I'll present some of our main results, which is on designing a new second-order algorithm and the results we obtained for this. Then I'll present some of the main ideas of the proof, and towards the end, I'll also explain in detail like a line of work which has started only like a few years back, which is on using these bandit optimization algorithms and extending them for solving control problems. And I'll again explain like the implication of our result to the particular setting of control with like linear dynamical systems. And finally, I'll conclude the talk with some open questions. Okay. So let me, by the way, so if there are any questions at any point during the talk, please feel free to ask them. I'll be happy to take questions as and when they arise. So let me first introduce the bandit convex optimization problem. So there are two players. So one is the, we call one of them the player, and then the other one is the adversary. And in each round, both of them pick their own choices independently. So the player picks a point xt. So xt will be data point in some space, let's say rd, and the adversary picks a convex function ft. Okay? And the player suffers loss, which is ft of xt. So ft will be evaluated at the point that was picked here xt. And then the player only gets to observe this value. And I guess like the adversary can then observe xt and then choose their subsequent loss functions depending on xt. That will be called the adaptive adversary. And if the sequence of convex functions ft are already chosen ahead of time, that's called the oblivious adversary. Okay. So the player in particular suffers loss ft of xt and only observes this particular value. It will not observe like the entire function ft. So this is where the term bandit comes from, because we only observe the value at the point that we actually played. Okay. And the player's objective is to achieve what is called sublinear regret compared to the best fixed point in hindsight. Okay, so let's first look at the blue one. This is just the average, the cumulative loss incurred by the player. So summation t equal to little t equal to 1 to capital T over capital T rounds ft of xt. So this is the amount of loss, cumulative amount of loss suffered by the player. And then we are comparing this with a min x over x of summation t equal to 1 to t ft of x. So we take the cumulative loss function, which is summation over t ft. And then we pick the best point in hindsight. So we pick a single point x for all the iterations t. But then, like, because we are doing this in hindsight, we actually can take a minimum over all the points in our set. Okay, this is our baseline, and yeah.
So this is going to change. It's going on capital T. Because you're summing over capital T.
Yeah.
The minimizer will change.
Minimizer can change as my things are evolve. So again, like there will be there are multiple variants here. So one variant is called fixed horizon, where you fix T in advance and then you are trying to minimize the rate only with respect to that particular T. Or you want to have like a no horizon. Basically, you want to have this kind of regret guarantee for every capital T. Capital T can even be arbitrary, and your algorithm has to continue to play. That's usually not that big of a distinction, except for maybe some constant. So usually, yeah. So this X can actually change with capital T. And for any point capital T that we have, for any value of capital T, we want this regret to be little of T, meaning that it has to be strictly smaller than a linear function in T. Okay.
It'll be interesting to see how it changes with the well study. Worst case, you choose the FT make X vary very much.
Yeah, that's a good point. Usually, if you don't care about constants, there is not much difference between. So, like the fixed horizon is clearly the easier version compared to any horizon. And usually, most of the algorithms that have been proposed automatically work for any horizon.
But can you say something interesting as a function of big C and increasing big T? How is optimal changing X of T?
So that depends on like how FTs are changing, right? And that's an adversary.
Yes. Are we very bad?
Yeah. So for example, in the first half of iterations, maybe you can make the minimizer to be 1 point, and then next round of points, you can completely try to make it something else. So yeah. So the point is like FT can be adversarial. They can change arbitrarily. We are not making any assumption like stochasticity or something. So the optimal X can actually change completely. Yeah.
You have extenuating assumptions. We have some bound that said the functions need to not work infinitely and so on.
Yeah. So the functions will be bounded and so on, but
you are making some assumptions here.
Yeah. So X will again be a bounded set and so on, but apart from that, the optimum can change actually like from one end of the set to another end of the set.
So here adversary get to see XT before choosing.
Adversary cannot see XT. So if adversary sees XT, then there is no way you can get sublinear regret, because there are very simple counterexamples. So we can say that the player will have a stochastic algorithm, and the adversary is aware of the stochastic algorithm. So all the adversary knows is that the player is going to pick an X from some distribution, but from that distribution, what X is going to be sampled, the adversary will not know.
Can there be simultaneous numbers both with XT and?
Yeah, this is basically simultaneous because so in each round, like both of them pick simultaneously, and then the adversary. Okay, so we want the player to achieve this for any adversary. So if you think from the adversary point of view, we want to have an adversary which actually maximizes this for any algorithm.
And not any adversary, right? You can get an adversary that maximizes FT at every iteration, basically possible to solve, but with some restriction on the regret.
No, I guess like the adversary can choose any convex function FT without the knowledge of XT. And our algorithm should be able to achieve this irrespective of what adversary we are playing against.
But it's fixed in hindsight, right? Like it's not minimizing X at every T.
Yeah.
Minimizing it.
Yeah, this is the baseline. Yeah, so this is the one that we are comparing against. Yeah. Okay, and within this, we can make a distinction, which is that if we are always playing XT, which is within the same constraint set that we are optimizing over here, it's called a proper algorithm. And if XT actually is not guaranteed to lie in X, you are maybe allowed to play things outside of whatever set you have. Then it's called as a proper algorithm. And this is in general, like this is much more general version of multi-arm bandits, which can be thought of as the same thing where FTs are linear functions, and you're only allowed to play like the endpoints of the simplex.
Constant functions are allowed?
Yeah, constant functions are allowed. So any convex function, like in this framework,
if there's a bound on the function, then every time if I use the constant with the maximum thing, then we will not be able to make any profit, right?
You will not have any regret because any point that you play will have exactly the same value. So ft of xt is, if it is ft of x is constant, then it doesn't matter what x you pick here. Ft of xt will be the same as ft of x. The difference will be exactly equal to 0. You'll have no regret. Okay, so yeah, so this problem has like a rich history and a lot of work. Now I guess like about 20 years since the first paper on bandit convex optimization came out. So the original paper which introduced this problem was by Flaxman, Pillai, and McMahon in 2004. What they get is that so all of these assume that the functions are convex, so that's fixed. If the functions in addition are bounded, like their absolute value is bounded, then the regret here, so which we wanted to scale like smaller than t, they proposed an algorithm which actually gets t to the 5/6 regret. So this is smaller than t, this scales slower than t. And for Lipschitz continuous functions, meaning that the functions have bounded gradients. They need not be bounded themselves, but they have bounded gradients. Then this can be improved to t to the 3/4. And then there was another very interesting result by Tiwari and Saha, where they improve this t to the 3/4 to t to the 2/3 for smooth functions, meaning that these are functions which have Lipschitz continuous gradients. So one order a higher level of smoothness. Okay. So all of these are kind of gradient based algorithms, and again like goes back to the work of Paul in stochastic approximation, where they were able to use like a function value single evaluation to construct an unbiased estimate of the gradient. And that's the underlying idea behind all of these works. The main difference is that that was done in the context of the same loss function or same map appearing again and again, whereas the main idea here is that we want to do this adversarial kind of optimization where the loss function that we are seeing at every time can actually change from one instance to another instance. Okay. So, so the best rate even for smooth functions turned out to be t to the 2/3. And then there was also a long line of work, even starting from like this original 2004 paper, to actually obtain like the identify what is the optimal rate and design an algorithm which actually achieves that optimal rate. And finally, so it was believed that the optimal rate is square root t, which is actually better than this. And initially, only for very special cases like linear losses and strongly convex losses, people were able to achieve this tight square root t rate. But for the class of general convex functions, this remained a outstanding open problem until Eldan, Lee, and Ubeck in 2017 proposed like a experts-based algorithm, which actually was able to achieve the square root t regret rate for general convex functions only under the boundedness assumption. Okay. So while this was really a breakthrough result, the main catch in this result is that the algorithm is actually very fairly complicated, and the dimension dependence of this general result is extremely large. Okay. So let's look at like this table of previous results. So each, yeah.
Yeah, so the optimal regret is in terms of like minimax optimal.
Yeah, this is minimax optimal. So if you consider like the worst case adversary, any algorithm has to suffer at least this much.
So again, sorry, any so in multi-arm bandits sort of results, there is something also like instance dependent, instance optimal results.
Yeah, so that's an interesting way. I am not familiar with like that kind of work in the bandit convex optimization setting, or even actually bandit linear optimization. So where like all these functions are linear functions. So it will be interesting to see if you can design adaptive algorithms for even like bandit linear optimization, bandit convex. Yeah, very nice.
Show the complexity. If you have linear losses, we direct get to complexity convex.
Sorry, can you?
So if you're in the convex setting,
yeah,
all linear losses suffice. It is get a guarantee of
linear losses. Yeah. But the thing is, linear losses are much simpler to deal with directly, and the algorithms are much more efficient. Whereas, like the general result for the convex setting is like very complicated, and the dimension dependency is extremely large. So, which we will see in this slide. So, each row corresponds to a paper, and then this column is basically what is the setting that they consider. And in particular, like this setting says whether they're adversarial or stochastic. Basically, FTs can change at every iteration adversarially, completely arbitrarily, or if it is not, like these two rows, for example, are stochastic, meaning that FTs are being sampled from some fixed distribution and that distribution is the same for all the iterations. Okay? And then constraints basically says whether your set has any constraints or it's an unconstrained optimization problem. And finally, like this is the regret and this is the running time. Okay. So firstly, we have this blue box, the last two ones, which are not adversarial, like which only can deal with stochastic losses, right? FTs come from the same distribution across all the iterations. The first five can deal with adversarial losses. But so this is not like a complete overview of all the results, but these are like a subselection of most related results. So as you can see, so the linear losses actually have like very nice regret and running time bounds, which is, so regret is linear in D. Next, so all of these have like square root 3, right? But if you look at the dimension dependence, like the regret here is linear and the running time is only quadratic in the dimension. So D is the dimension of the points that you're playing with. And similarly, like for strongly convex and smooth, like the algorithm is again like gradient based and it's very simple. But then like even when you go to quadratic, the best regret bound that we knew for or like, so this particular paper gives a regret bound of d to the 16 and then there's a d to the, so d to the 4 in the running time. And again, like the Bubek et al. Paper, which is the algorithm which works for like the most general convex function setting, the dependence on dimension is extremely large, like in regret and in running time as well. Like the polynomial is here is extremely large. And more recently, there was a paper by Latimore which managed to improve the dimension dependence in the regret, but it actually paid a huge cost in the running time. Like the running time actually went from poly in D to exponential in the dimension.
So when you assume bounded, is the bound known or it just has to exist?
Bound usually we assume to be known. Yeah.
It's not like it's unknown, but it's still, if it's larger than the complexity.
Yeah, usually these papers, I mean, yeah, they assume that the bound is known. It may be possible to kind of use some simple trick to generalize it to when the bound is unknown, but I'm not, because like you also observe like the losses and so on, right? And based on them, maybe you may be able to estimate a bound and then, yeah, yes,
The bound appears in this expression? No.
sorry?
Does the bound appear in the regular expression?
So this is the bound for regret.
No, this is the dimension.
Yeah.
All I have to let me rephrase it. Maybe I'm not clear. So does that O tilde hide some constants?
It hides some constants and also logarithmic factors.
So that constants have this bound on the loss count? No.
The constants, yeah. So I'm not explicitly denoting like what the dependence on like the boundedness part and so on. Yeah, there are those dependencies also, but I'm not showing them here. Yeah.
So one other quick thing, maybe I mistake. What are the constraints? What do you mean by?
So constraint is just whether like this X is bounded or I mean this X will always be bounded, but you can also consider like an unbounded
Feasible space.
Yeah. Whether the feasible space is given by constraint set or it is just like all of RD. Yeah. No, quadratic can have like very close to zero condition number. You may even be linear in some directions. Yeah. Okay. So yeah, so for stochastic, I guess like there are more efficient algorithms that do exist, but it turns out, and also when we go to the control application, we will see that adversarial is really very important even beyond stochastic. So actually improving the dimension dependence in these results, even for the adversarial setting, is what we want to consider. And in particular, like the first question we ask is whether we can design a simple and efficient, meaning that there is low dimensional dependence on both regret as well as runtime for a large class of convex functions. Okay.
So stochastic meaning this function f is coming from
some underlying distribution. So it will be,
parametric form or
sorry?
some kind of parametric form of f function or?
No, it's just like a fixed distribution across all time instances. So in particular, like our optimum cannot move.
But somehow you learn the distribution as well when you do this.
No, actually, I think like it basically relies on the fact that your optimum x does not move too much. So you can continue to localize the optimum in like smaller and smaller balls. So that's the main idea of like these stochastic ideas. Whereas in the adversarial, the key challenge is that your optimum can just move from anywhere to anywhere because your loss functions are actually adversarial.
You could have a layer where you say, okay, my stochasticity is not so much lag and learn. That was what
Yeah, so that will be different. I guess like maybe you can say within stochastic, maybe it's also linear, right? So stochastic linear. So particularly for logistic regression, like there has been a lot of work on bandit logistic regression. Most of that is in the stochastic setting. Okay. So hopefully the question is clear. So which is that you want to design like a simple and efficient regret as well as runtime algorithm for a large class of convex functions, even if not like the most general algorithm in this Dubek et al. Paper. Okay. So in this particular work, we consider what are called kappa convex functions, and our results will be for this kappa convex class of functions. So a function is called kappa convex if there exists like two constants, little c and capital C, so that and then like a positive reference matrix H, such that my Hessian is always sandwiched between little c times H and capital C times H, and the ratio capital C divided by little c is at most kappa. Okay. So this actually is includes like a large class of convex, like special classes of convex functions that have been previously studied. So for linear functions, we can just take H to be equal to 0, right? So our Hessians are always equal to 0, and C, little c and capital C can be taken to be 1. So linear functions fall into this with kappa equal to 1. Similarly, if we take like generalized linear functions where we apply like a monotone nonlinear function phi of c comma x. So for example, we can think of logistic regression here. This again, so in this case, like the Hessians everywhere will be rank 1 matrices in the CC transpose direction. Again, depending on like the range of phi and the dimension of x, we can again, so that will determine like the kappa here. But still, it turns out that like generalized linear functions are also belong to this kappa convex function. Okay. Sorry, yeah, this H and this H is the same. So basically, you have some kind of H. It can be 0 in some direction, so it's only need to be positive semi-definite. So no, this is a little c and capital C, so they can be different. Yeah.
No, but in terms of like as functions of x, so if f of x is not x, like t is not of x.
Yeah, I mean, I'm not saying that this comprises like all convex functions belong to this. I'm not saying that. I'm saying there are interesting classes of convex functions which actually are kappa convex. And examples are linear functions, generalized linear functions, and also quadratic functions. And where like A actually does not need to be positive definite even. It can even be positive semi-definite.
So different sets would leverage different problems.
Yeah, I mean, for now, we just assume that we have a bound on kappa, and that's basically all we assume. Like the algorithm only needs to know a bound on kappa. It does not need to know what H for which this is satisfied and so on.
Functions that are strongly convex and have lipstick.
Yeah, strongly convex automatically fall into this category.
Lipstick gradient also.
Strongly convex and smooth, for like they fall with a condition number of kappa, they fall into this category where H you can take it to be identity. Yeah. No, F is convex. So the entire talk, sorry.
Then only we can compare with the P of capital N, because which is the positive statement. And then only we can compare it. Like you were telling that then can be convex, not convex.
No, I said strongly convex or not strongly convex. So F is always convex. But if it is not strongly convex, it means linear functions are not strongly convex, even though they're convex. Yes, question.
Can H depend on X?
Can X depend on?
H depend on X?
No, H is something that holds uniformly within the entire domain. Okay. So this is the class of functions that we will consider, and hopefully I have convinced you that this is this comprises at least like several interesting classes of functions. And even if you look at like just logistic regression, there are several works which have tried to identify what is the optimal regret bound that we can get for just like online bandit version of logistic regression and portfolio selection. Like many of the very well studied problems, like they do fall into this category. So we will focus on designing efficient algorithms for the class of kappa convex functions. Okay. So the first main result is that we actually can propose an efficient bandit Newton algorithm. I'll like describe the algorithm in more detail in the next slide for kappa convex functions. And informally speaking, what it gets is d to the 2.5 times kappa square root t regret and d square per step running time. Okay. And in particular, like if we extend this to like well-studied problems within the generalized linear function setting. So for bandit logistic regression, this guarantee is like d to the 2.5 e to the 2d square root t regret, where this capital D is the diameter of the domain that we are working with. And again, like the runtime is again d square per step. And the second contribution, like if we again like specialize this for the setting of like bandit linear regression, then we actually get like a very efficient algorithm which has d to the 2.5 square root t regret and a per step running time of d square. Okay. So the second one, this does not have any conditions on x. So here, this capital D is the diameter of the constraint set x. Okay. I mean, the reason this comes up is because like this e to the d turns out to be like the kappa condition number of the problem, and so kappa square is basically 2. Okay. So let me go over the bandit Newton algorithm. Yeah, so maybe looks like it has a lot of lines, but hopefully I can convince you that, hopefully I can convey like the main ideas. So this is anyway, like we first initialize, start with some point, and we keep a running sum of like the Hessians that we have encountered so far, right? Which is A0 twiddle, which we start with identity. And in every iteration, what we do is we sample two different vectors randomly from the unit sphere, like the surface of the unit sphere. And then we play a point yt, which is xt perturbed by vt1 plus vt2, but with this particular norm. So we have this A0 twiddle here. So we'll maintain like a running average of like the overall Hessian that we have seen so far, regularized with this identity. And then we perturb the point xt with like in a direction in this ellipse defined by at minus 1, and in this particular direction vt1 plus vt2, which was like both of which were chosen random. And then we play this point yt, and then we observe ft of yt. This is the only information that we get. And then using only ft of yt, and then the perturbations that we have done, which is vt1 and vt2, we actually construct like a gradient estimate grad twiddle t, and then a Hessian estimate H twiddle t. So it will be used in setting like the step sizes like eta. Oh, sorry. So this kappa prime is like an upper bound on the condition number. Script K is actually the convex set, like the constraint set. Yeah, it was X. Yeah, sorry for the change in notation. Yeah, so this K is just the constraint set. YT will not. So the algorithm that we will design is improper. So, but then we will always compare with like the best action within that. But one thing I can say is that YT will never be like very far away from the constraint set either. We can actually bound like exactly, at most we'll go by how much amount outside of the set. Yeah.
These gradient and the same estimates that you are computing, this is for which function? Is it a P or is it like the sum that you have?
Yeah. So for general kappa convex functions, it turns out that it does not have a very simple interpretation. actually this gradient turns out to be the gradient estimator of one kind of smoothing. And this is the Hessian estimate of a slightly different function.
But this is not FT.
Both of these are not FT. So basically, if we take an FT and then we take for every point, we replace the expectation of FT in a small ball around that point. So these are various kinds of smoothing, depending on whether you're choosing a ball, you're choosing an ellipse, what is the diameter, and what's the size, shape of ellipse. So, and then again, whether you're averaging over the entire interior of the ball or only over the surface of the ball. So you get different kinds of smoothings. This gradient, it turns out, is the gradient estimator of one kind of smoothing. This Hessian, it turns out, is the Hessian of a different kind of smoothing, but they are related. And so that's a complicated part I did not get into. But if we just think of quadratic functions, so if FT were just quadratic, then this gradient is exactly the gradient estimate of the current function. And this Hessian is also exactly the Hessian estimate of the current function. Sorry, what is the global bound on YT? Lower bound. So YT is a vector.
So this XT plus.
XT plus. Yeah, this is a perturbation. This is because we kind of want to estimate basically the gradient at XT. But if we just observe the value at XT, we don't know what the gradient can be, right? So we perturb the point XT randomly and then get a different point YT and then observe FT of YT. And using FT of YT and then the perturbation that we have done, we can construct some unbiased estimators of the gradient and Hessian. But again, as I was saying, like this will not be of the original function, but some smooth versions. In this case, actually different smooth versions. But for quadratic, like both of these will be unbiased estimates of gradient and Hessian of the original function. Yes, sir.
Sorry for a very dumb question, but for the idea of step 4,
Yeah.
is that you already have FT or XT from the previous subject.
No, we don't have. So that will be FT minus 1 of YT minus 1. That's what you would have had.
So then how does this help you to estimate it?
So maybe it's so it may be easier to see for with a linear function. So if FT was linear, so it's just inner product of C comma X, let's say, and instead of X, you are putting sorry C comma Y, and then you're putting this entire thing. Now when you take C, so this FT of YT will be C, C is your, or G is your gradient. So G comma this entire thing, and then when you take G inner product of G comma V times VT1, and then you take an expectation over VT1 VT1 transpose, that comes out to be identity, and then this will exactly be the gradient. And like the same kind of argument holds for like the Hessian estimation, but this only holds for like quadratic functions. Beyond quadratic, these are not unbiased estimates of gradient and Hessian for the original function, but they correspond to some estimates of the some smooth functions. Then like we have to account for the smoothing.
How is A tilde T varying as function of T?
So yeah, so first we compute these estimates, okay, and then we update like our cumulative equivalent T by equivalent T minus 1 plus whatever Hessian estimate we have at the current iterations. Okay. So we are trying to keep track of all the cumulative Hessians we have seen so far, and then putting it into equivalent T with this scaling factor, and then we initialize it with identity to act as a regularizer.
No, but previously you have a set for its varying XT.
I mean, it depends on what your functions are, right? Because I mean, intuitively, it basically is trying to just capture what are the sum of all the Hessian of the cumulative function that you have seen so far.
Within some sense, you have to kind of, when you're dealing with adversity, you have to kind of see what's the optimality of stock right now. But you also want to keep it slightly more random so that in future the adversity can't.
Yeah. So basically, whenever you have a cumulative Hessian, which is very high, then your loss surface looks very like a very, very deep valley, right? So you don't want to explore too much. And this equality, because we are keeping track of like what's the cumulative Hessian, it's telling us how much you can explore. And in particular, yeah, so basically this exploration is driven by this equality minus 1 to the minus half. So if you are in a very, very steep valley, then you don't want to explore too much, because if the adversary, the loss is already like very concentrated, so the optimum would not be very far away. Whereas if like the loss functions are all linear, then equality will almost always be just close to identity. So you're always exploring in like the same kind of ball in all the iterations.
Your Putting the grad at XTS. Because so far you talked about YT.
No, we only observe FT of YT. This is an unbiased estimate of the gradient, not of the original function. It will be of some smooth function at xt, at xt, at xt. Yeah.
When you got X1 started, so you got a YT for charge. Down the line, you are updating the XTs.
Yeah. Yeah, and then like we update xt plus 1, basically we take something like a Newton step. So this is why it's a Newton kind of algorithm, where we are taking like the cumulative Hessian inverse times the gradient estimate, and then we are again projecting back onto the constraint set xt plus 1. So xt's will always be in the constraint set. Only yt's, when we do this perturbation, might actually go outside a little bit. Yes, Prashant?
Question, why is second order information system is very, I mean, situation was if I get rid of 80s and there's no gradient descent, do I get regret?
Yeah.
Just for 3 or something.
So yeah, T for 2 over 3 for smooth functions, yes.
When, no, I mean, not the general one, but it's kappa convex.
I guess we don't know how to take advantage of kappa convexity without actually using the second order information. The best, like the only applicable result that I can think of here directly is the T to the 2 over 3 for smooth functions.
But that's general.
That is general, yeah. Yeah, I don't think you can use kappa convexity without using, yeah, but there is no lower bound either.
No.
Yeah.
Can you get lower bounds on this? Dimensional lower bounds?
Yeah, actually, that's an interesting point. I'm not familiar with like the correct dimensional lower. I think like linear and it like there are very tight lower bounds, but beyond that, yeah, I'm not. Okay. So I'll go over the main ideas of the proof. Maybe like this slide and the next slide will be the only more equation filled slides. So for now, like let's just consider like quadratic function. So ft of x is x transpose htx plus ctx. So ht and ct are arbitrary, right? Now we initialize like a equal to 0 to be the identity matrix D cross D. And for this particular case, it turns out that this gradient and Hessian estimates that we were doing earlier for the quadratic case turn out to be exactly the gradient and Hessian, like unbiased estimates of the gradient and Hessian of at xt. Okay. And this can be done explicitly because like we'll only get some Gaussian terms and then like all the odd terms vanish and only the even terms. Okay. And then like we update a equal t as a equal t minus 1 plus eta h equal t, right? So now if we consider the potential function that, so we fix any x, so x is arbitrary, and then look at xt minus x in the a equal t square norm, okay? Then what we see is xt, so firstly xt, again, like let's ignore like the projection step, is just xt minus 1 minus this Newton kind of step here, right? And in the, this is in the a equal t norm. Now when we expand the squares, we get xt minus 1 minus x a equal t square, so that's this term. And then this inner product with xt minus 1 minus x, but then this a twiddle inverse cancels with a twiddle. So we just get like the usual inner product here. And then finally we get like the norm square of this again in the a twiddle t norm. One of the a twiddle t inverse cancels, and then we get this particular term. Okay, so now if we expand this term, because a twiddle t was a twiddle t minus 1 plus h twiddle t, right? So we just expand the squares here into these two terms. And this is basically the same potential function from the previous iteration. And we only need to worry about like this remaining term, right? So firstly, like this expectation of this h twiddle t term here, because xt minus 1 was already fixed and h twiddle t is random, is an unbiased estimate of ht conditioned on xt minus 1. So the expectation of this is exactly xt minus 1 minus x in the ht, which is the actual Hessian square. So when we combine these two terms with h twiddle t replaced by ht and then this gradient term, and if we use kappa convexity, we get that this is actually upper bounded by minus eta times like the function values of optimality compared to xt and x. Okay. So this is the only place we are using kappa convexity. And finally, like we have this additional term, which is g twiddle t, a twiddle t inverse g twiddle t. If you recall, like the definition of g twiddle t, it had a twiddle t to the half, right? And so basically this ends up being O of 1. So if we telescope this entire thing, what we get is that like the cumulative suboptimality compared to any fixed point x is the initial distance x0 minus x squared divided by eta plus eta times t. And so if xt were the point that we played, like this automatically gives us the regret that we want, and this is the kind of standard regret bound that we get in online convex optimization. Okay? But xt is not the point that we played, but rather like we actually perturb it using this particular term, and right. So we perturbed it using this particular term, but it turns out that we can bound expected value of ft of yt compared to ft of xt by using like the trace of ht, which is the curvature around xt, times the amount of perturbation that we are making here, which is ht times atotality inverse. Okay, and because atotality is kind of accumulating all the ht's one after another, we might get a ht which is very large in one particular iteration, but then the next atotality will actually would have absorbed ht. So by doing like a standard argument using log determinant, so we get that like this entire summation over all the iterations can grow only as square root. Okay. So the same, like this bound cannot be made to be large in every iteration, because in some iterations, if it is large, it means that ht has to be large, which means that in subsequent iterations, atotality would have been large, so its inverse would be small. So that's the averaging effect that happens.
Why we need to why we need to sample?
Why we need to sample like this? So as I was saying, so atotality is basically estimating the Hessian of the cumulative loss function. So if the cumulative loss function is Hessian of cumulative loss function is very high, so it's like very, very sharp. So the minimum is like in a very, very sharp value, right? If you perturb even a little bit, you are going to suffer like a very large amount of suboptimality, right? So you don't want to perturb very large if the cumulative Hessian of the thing was very large. If the cumulative Hessian was say 0, which is in the linear function, you can actually always do a lot of exploration because suddenly your minimum can move very far. Whereas in the cumulative, like if the cumulative Hessian was large, your minimum cannot move very fast in very quickly. Yeah.
So I want to know why do you need this VT1 and VT2? So my guess is you're somehow trying to compute the gradient. So if you're at xt, you do xt plus delta, xt minus delta, and somehow the values are there, but it's not clear what is the role of.
So that's a good point. Yeah. So if you only care about gradient estimate, yes, only one perturbation VT is sufficient. But because we want both gradient and Hessian, so that's why we end up needing like two.
But we estimates for the gradient instead of one. We are using VT1 only in the gradient. Can we use VT1 and VT2 both and have
up to constants? Yeah. So maybe the like you can get maybe a variance reduction. I haven't. Yeah, that's a good point. I haven't carefully thought about. But I think like maybe you can only get some constant factor improvement in the variance probably. But I wonder like if it interacts with like the Hessian estimation and.
You're only getting one function sample, so you need to add more reduce.
No, I guess like the question is you can take VT1 plus VT2 to be the net perturbation, and then use that as your overall perturbation in the gradient computation step. Whereas currently we are only using like VT1. We are not using VT2 in the. Yeah, I think like that can reduce the variance a little bit actually. Yeah. Okay. So in the
Question. If you don't know the value of kappa when you're evaluating this statement to what? It's like not knowing a literature.
we need an upper bound. At least you need to estimate. I think, yeah, I don't know how to make it work without that.
Optimization, even if I don't know the movements.
So
I can still work on.
the issue is like there, maybe it's you're considering like the same function appears multiple times. So you can do something to figure out like the smoothness on over multiple iterations. You're getting each function only once here. And I don't know how to estimate that with.
Not getting the same.
Yeah. So in the remaining part of the talk, so how much time do I have? 15. Okay. So in the remaining part of the talk, I want to explain the application of this result to like control. And this is actually a very recent line of work, recent being maybe 5 to 6 years old, and initiated 5 to 6 years old. And the main idea is how to use the adversary, like the sophisticated algorithms for this bandit optimization, which can actually work with like adversarial loss functions and so on, and use them to design better control algorithms, which are maybe more robust in some ways, which we'll see in a little bit. So, and this line of work is basically what is called online non-stochastic control. Actually, like the next maybe 7 or 8 slides will be about giving an overview of like what online non-stochastic control is and how bandit optimization, bandit convex optimization actually can help in designing control algorithms. And then at the end, I'll just state the result that we have, which basically applies the previous result with some more things that we need to do to the control setting. So yeah, so firstly, as this picture depicts, like the online non-stochastic control basically sits at the intersection of like reinforcement learning, or also maybe we can say control, where like we don't know the dynamics, and then online convex optimization or online bandit optimization that we have been looking at so far, and also like convex relaxation to design like computationally tractable algorithms. So the basic formulation of control is that we have a dynamical system with some internal state xt, and then we are giving some control outputs, control inputs ut, and then there is some noise which is perturbing it, which is wt, right? And the system evolves as xt plus 1 is f of xt ut plus wt. So f can be the system that's actually driving the system. F is a function that's driving the system. And then we care about, like, after t steps, we want to minimize the cumulative cost ct of xt comma ut over all the t iterations. Okay? And xt is the state, ut is the control input, and wt is the noise that we see in each of these. Okay? So in particular, if we make the f explicit, and we in particular like specialize for the linear system, where xt plus 1 is actually a linear function of xt as well as the control input ut, and then the noise is also added linearly to this, then this corresponds to linear dynamical systems, and this is the prototypical like optimal control problem, right? And in particular, like if we further assume that wt is random, right, for the stochastic noise setting, this has been very well studied, and in particular when ct is actually quadratic. So this is the problem of linear quadratic regulator, where again, so this is all classic results. So we know that ut, the optimal control input, turns out to be matrix kt times xt, so it's a linear policy. And the kt is actually given by the algebraic Riccati equation, which depends on like all the cost Hessians that we have here, as well as like the AT and PT matrices that are actually driving the system, right? And the main idea is that we can write like the Bellman optimality equation for the system, and then prove with backward induction that the optimal value function is always quadratic, and so the optimal policy is always linear. Okay. Now, if we relax this assumption that wt is linear, wt is stochastic or Gaussian, to wt can be arbitrary, then that basically leads to the problem of H infinity control, which is also called like the robust control problem, which again has, it turns out that the optimal control input again turns out to be a linear function of the state. And the main issue with this is that we're actually designing a control system which always anticipates the worst possible, which always anticipates the worst possible noise vectors wt. Okay, so even if the noise vectors are much more benign and actually stochastic, this like the H infinity control problem cannot actually take advantage of the stochastic nature of the noises, and not which is not adversarial, because it's explicitly designed for working well with like adversarial kind of noises. In particular, it cannot get any better results compared to what it can get with adversarial noise. So the idea from the bandit convex optimization or online convex optimization setting is that whenever we are looking at the benchmark that we are comparing with in the regret context, that's always adaptive. So we are taking a min over x for the cumulative loss functions that we have actually encountered. We are not treating them as like the absolute adversarial loss function. So we are not we are not taking a max over all the loss functions and then we are optimizing for that, but rather our comparator actually depends on the cumulative loss function that we have encountered in the function, right? So this leads hope that we can actually do maybe a regret based analysis where we are competing with respect to the best policy in hindsight for the given noises as opposed to the best policy for the worst possible inputs, right? And we also want to design like efficient methods for general loss functions that we have.
So this is for like teaching critical. There's a stochastic problem.
Yeah, so stochastic problem is not robust. If you give like adversarial noises, it will not work. The adversarial problem is just always focusing on the adversarial. If you give stochastic, it cannot do any better compared to what it was doing in the adversarial setup. Whereas the online convex optimization framework lets you compete with a optimal policy in hindsight, which actually depends on the realization of the noises that you actually encountered during your work. Okay? And like a simple example would be that if you are flying a drone from like a particular source to particular destination where we don't know the weather, the optimal robust control theory, so the H infinity one will optimize for like the really worst possible conditions and will operate as if like that's the current setup. Whereas the H2 setting, which is like the optimal control with the Gaussian noises, it will be overly optimistic, assuming that my wind conditions are like very favorable, right? Okay. So the goal of adaptive control is to get best of both worlds, basically to compete even with H infinity in the worst case scenario, but at the same time, when the situation is not as pessimistic, then we are actually doing much better compared to like the overly pessimistic setup. Okay. Okay. And so in this framework, so I guess like we have XT plus 1 is like this is a dynamical system that's running, and we don't have access to exact XT, but we may have only access to YT, which is the observation. And then our cost will be only in terms of like the observation YT, and then the input that we are giving, which is UT. Okay. And in particular, like this WT is what we will make either adversarial or stochastic. We don't care, but we want to compete with the best policy in hindsight. If we were seeing the same WTs compared to the optimal policy in hindsight for the same set of WTs. So yeah.
IT is a measurement policy. So you that as a IT.
Yeah, this can also be adversarial. So both of these can be. Yeah, actually, I think like only WT can be adversarial. This is probably stochastic. So the observation is always stochastic, but it's a measurement noise. So that's stochastic. The only one that's actually driving the system, like that part, that can be adversarial. Yeah.
You show some law on this ITs then.
Psyche, I think like we just assume zero mean and yeah, maybe actually light tail kind of assumption.
Oh, even on the conditions on the tail.
Yeah. Okay. So the framework is the following. So we observe YT, which is observation, and then based on that we play control UT. So this is the algorithm. This is what the algorithm needs to do, and then it incurs loss CT of YT comma UT, which is what it observes. So it doesn't observe the entire sorry. So it doesn't observe like the complete loss function. It doesn't know beforehand, but it only observes like the loss at the current point. And then we want to minimize the regret with respect to the best policy in hindsight. So pi is the best policy, and this trajectory has the same sequence of WTs that was encountered here. No, so I mean the control problem basically you play some UT now, it affects like where you're going to go next. But the optimal policy could have done something else, it would have gone somewhere else.
But like AT and BT, they are again like
No. So actually, AT and BT need not even be symmetric. Yeah, so that's a good point. So you cannot reduce this problem to strongly convex. So even if you assume that the cost function CT is actually strongly convex in terms of YT and UT, the overall problem in terms of will come to like how we frame the problem, like that will not be strongly convex. So we do assume CT is strongly convex, but this is far from guaranteeing that the eventual convex optimization problem that we are going to deal with is actually strongly convex. So that will not be the case. Yeah. So here I guess like we want to compete with respect to the best policy in hindsight for the same set of like error vectors. And so in particular, like what do we take this minimum over? So one, yeah. So in general, like there may not be an optimal policy that's fixed beforehand because like we are dealing with adversarial noises and we only know the optimal policy in hindsight. So the kind of policies that we can compete with, like one example would be just linear policy. So you take any policy where the control input is just a linear function of xt, right? But xt is not available, so it will be k times yt, right? And so this will be if xt was observable. And then there will be linear dynamical controllers where your control input itself actually evolves as a linear dynamical system. Okay. And then again, you will, so you can choose any possible A, B, C, D, which basically, sorry, it should be D. So this basically gives you all possible classes of linear dynamical controllers. And then there are disturbance action controllers, which basically depend on like all the past disturbances WT minus I, right? But the issue is like we don't actually know what the disturbances that we have are. And what we can only rely on is like the YT minus I, which we have observed. And in particular, like this YT minus I NAT basically denotes the observation that you would have had if you had given just 0 input, but with the same set of noises. Okay. And it turns out that if we know the system dynamics, A, B, C, and D, then we can actually simulate these natural responses. So basically, linear policies are like the most constrained, and linear dynamical controllers are slightly larger. And ideally, maybe we would like to do this disturbance action controllers, but we don't know how to do WT minus I. So we can at least compete with like disturbance response controllers. So this will be the class of policies that we will optimize against. And so maybe I'll just wrap up in the next 5 minutes. So there are two key ingredients I want to highlight. So one is that we want to do convex relaxation. This is not due to us. This again like due to prior work, where if you do the disturbance response controller or disturbance action controller, because of the dynamical system where you are driving it with, where comparing to the policy K with 0 inputs, then it turns out that you have like this A plus BK to the I times. So this is the matrix that you would want to multiply with the disturbance that you got in I steps prior. But we don't know how to optimize this because this is a non-convex problem. So we can relax A plus BK to the I to any arbitrary matrix Mi. So this is a convex function as a function of M. Okay. So this is now a policy which is a function. So these M's basically determine what your policy is. And second, we need to actually extend the bandit convex optimization approach to playing with memory. What memory means is that the player first chooses YT and then the adversary also chooses say FT plus 1 M, which is like M steps ahead loss function, which means that FT was already chosen. But the player basically suffers a loss which is not just dependent on FT and YT, but rather also like the past M iterates that the player has played. So there is this notion of memory, and what you did in the past can actually come back and affect you in the future. And in this context, again, like the comparator is using the same Y all throughout. So this is what is called bandit convex optimization with memory. And the reason memory comes up is because control systems have this memory. Whatever input you have played earlier actually has an effect on what you're going to do, see in the future. So firstly, we have a lower bound which says that if you just consider like this general bandit convex optimization with memory setting, even for quadratic functions, online bandit quadratic optimization, even with like memory length n even equal to 2, then the regret has to be at least t to the 2 over 3. So this is a minimax lower bound. Okay, so you cannot get square root t regret for the general bandit quadratic optimization with memory setting. And in particular, like the hard instance that we develop here builds upon like a previous instance initially presented in the Deckel et al. Paper in 2014, who only considers 0-1 cost, but we are able to extend it to continuous cost, and in particular go to like the quadratic cost here. And there is an algorithm which almost gets a matching upper bound in Castle and Coren. So it seems like this is a tight bound for bandit quadratic optimization with memory. And the question is whether this is the best we can get even for the control problem that we described earlier, right? But it turns out that the control problem, when we reduce it to bandit convex optimization, it has a final structure where the memory component appears only in the affine part. So it does not appear in the quadratic part, but only in the affine part. What I mean by that is that the player chooses this YT and adversary chooses FT, right? And the player actually observes, like, has a full information of the cumulative Hessian part, right? And what the player has only bandit information is about like the KI part, not separately, like we observe like this entire thing. But the point is we have this additional information where we have this summation I equal to 0 to m minus 1 HII, which is the cumulative Hessian if we consider it as a univariate, like if you put the same Y's in all the places. Okay? And so this particular reduction is actually due to Simchowitz from the paper by Simchowitz in 2020. But once we have this like affine memory reduction, so I'll not go over the things here. But it turns out that we can actually upgrade the Bandit-Newton step algorithm to achieve like square root regret here. The main idea is that in the memory context, we no longer have to do the Newton, like the Hessian approximation exactly, but then we already have that information and then we can still do the Newton step method. Okay. So these are all the previous results, and basically what we are able to do is, so the best known result is by this Sun et al. Paper, which was at Europe 2023, where they were able to deal only with semi-adversarial noise and were able to get like O2 of square root t for the partial observation setting. We are able to generalize this to complete adversarial setting while still getting the square root. So just to conclude, so we presented like simple and efficient Newton algorithm for bandit optimization with like efficient, like with a mild dependence on both the dimension as well as the condition number of the convexity. And we can actually extend this algorithm to get an omega 12 of so this should have been O of square root t. So we can then extend this algorithm. Both of these should have been O. So we extended this to the LQR and LQG problem, which again gets a square root regret. But for the more general problem of like bandit convex optimization with memory, we have a lower bound of t to the 2. So there's certainly some interesting open problems here. Like firstly is that the algorithm that we propose is not proper, meaning that we end up playing points outside the constraint set. So designing a more like proper BCO algorithm, which only plays points with the constraint set, will be very useful, and in particular is required in order to extend these results to online portfolio selection, where like it doesn't make sense to take a portfolio which is outside of like the simplex. And again, like going beyond kappa convexity to more general class of functions seems very interesting. But the main challenge is that the Hessian is actually only useful locally in general, and kappa convexity enables us to use like the Hessian estimate in a more global fashion. And again, extending non-stochastic control with more general losses, which is not quadratic, for example, like generalized linear losses, again sounds quite interesting. And extending the bandit quadratic optimization with memory lower bound. Currently, the lower bound is applicable to only non-oblivious adversaries, adaptive adversaries. So if we can generalize even to oblivious adversaries, that will again tell us like the limits of what we can do with bandit information along with memory. That's all I have. Thank
you. One quick question.
So in the online control problem, what space is it that you do the Newton step?
Yeah.
MI.
Yeah. So M's are my variables. So these M's are my variables.
Restrict yourself to the finitely many of them, or that will be absolutely.
So basically there is a dependence on, so firstly you have A plus B, and then you will have to find something called a stabilizing control K. And then once you have A plus BK, the largest singular value of this, like how far it is away from 1, that tells you the kind of amount of memory that the system has. And so you can take a memory here, which is that times maybe a logarithmic factor. Yes, question? Yeah. So FT, so if there were a single y, this is exactly the same as the previous regret, right? Because we are taking the cumulative loss function, and then we are minimizing a y in hindsight. In this case, y is like a policy, and we are saying for the control problem in the entire duration, I'll use a single policy, and that policy can be whatever arbitrary. So we are taking the best policy depending on the loss functions that we have observed the duration. So this is basically the best policy in hindsight.
Okay, so maybe in the interest of time, we'll.